Most third-party libraries and applications have been tested with this. Chances are people you find everywhere on the net have done this before, even if there are people who are currently using something else and can help you with any problems you run into. So let's take a look at each of the components and where it makes sense to stay with the traditional way and where it makes sense to change things. First component is binutils. That's a collection of tools that deal with object files. So even if you haven't used binutils directly, you have used it indirectly because your compiler makes heavy use of it. For example, if you have multiple C source files, your compiler generates object files and then binutils is used to link them together into the final executable. There are three major implementations of binutils, and actually chances are you have all of them installed on your computer right now. First is the standard implementation GNU binutils, which has been around for decades, which is what everyone has been using traditionally. Then there's elfutils, which is shipped with almost all distributions, so they can get the libelf component that is used by a couple of third-party applications. And then there's LLVM binutils, which is part of LLVM, and LLVM is built pretty much anywhere because it's needed for Mesa drivers and things like that. So chances are all of those three components will be on your system already. Let's take a look at each alternative. Elfutils has a pretty good implementation of everything it provides, like object dump, object copy, but it doesn't have a linker, which is one of the more important parts of a tool chain. So using just elfutils will not do. You will at least need the linker from binutils or LLVM. The tools in GNU binutils and LLVM binutils are pretty much interchangeable. They use the same parameters. They are drop-in replacements for each other, with a couple of slight differences. And the LLVM tools have one big advantage: the cross compilers for all targets can be built in. So if you use the LLVM version of object dump to disassemble an object file, you will get the right output regardless of whether that object file is an x86 file or an ARM file or a RISC-V file or whatever is supported in LLVM, which is just about every processor target you could find. Whereas with GNU binutils, you need different versions of the tools for every target. The other key component is the linker. GNU binutils used to be ahead there. LDBFD and LD Gold were pretty much the only available options until not too long ago. But in LLVM 10, the LLD linker has pretty much caught up, and it only got better since then. In LLVM 11, 12, and 13, there's not much of a reason to use any linker other than LLD. And with LLVM 14, it's seeing even more new features, like the better RISC-V support that will make it possible to use LLD for just about everything. The next thing to look at is compilers. For a long time, GCC was the only compiler that could seriously be considered, and it still does a great job. It's still a really good compiler. It supports all important programming languages, supports all important targets, almost always supports latest versions of languages, optimizes pretty well. But there's other good options. One of them is Clang from the LLVM project. It also supports a lot of important languages, and it's being used by some languages that are available out of tree for LLVM, like Rust, Swift, and Pony. They're all built on LLVM as a backend. It supports all important processor targets and a couple of other interesting targets like GPUs, WebAssembly, and BPF. It also supports the latest versions of languages and optimizes very well and has many sanitizers. One interesting difference between GCC and Clang is that Clang is a cross-compiler by design. So whereas with GCC you have to build a cross-compiler for every target you want to support, with Clang you just build it once and you can just use dash target whatever machine you want to target, regardless of what machine you're on. the one Clang binary will compile for every target. And another advantage of Clang is that it's much easier to get into Clang's code than into GCC's code. So if you are planning to work on the compiler itself, Clang is an interesting option to look at. Performance is pretty much similar to GCC. If you build with -02 or -03, some things will run faster when built with GCC, some things will run slightly faster when built with Clang. Overall performance is really similar, so unless you're doing something really special and you want to run your own benchmarks on it to make sure you're using the best compiler for exactly what you're doing, just from a performance perspective, there's no real reason to pick one over the other. The initial release of Clang was in 2012, whereas GCC was released in 1987, which explains many of the differences already. When GCC was first released, there just weren't as many good tools available as there are now. So Clang has a couple of advantages in being able to make use of things that just didn't exist when GCC started. Another difference is licensing. GCC is GPL, Clang is Apache 2.0. Both of those licenses have their drawbacks and their advantages, so you want to check for yourself what you prefer. Of course, there is a good chance you will need LLVM anyway because you will need Mesa, but on the other hand, depending on some other decisions you will be making for your toolchain, you will probably need GCC as well, even if you opt to use Clang, because of libstdc++ and libgccs, but more on that a bit later. One of the interesting things about Clang is that it's really modular code, everything is built into libraries, so if you are planning to build something yourself around the toolchain, like an IDE or so, Clang makes that a lot easier by being able to link directly into your code. One good thing about both Clang and GCC is that they are binary compatible, so you can use a library that was built with one compiler with the other, and you can even build one particular object file with GCC, another object file, part of the same application with Clang, and then link them together with either of them, and the result will work. There's usually no reason to mix compilers that way, but it is possible. If you do that, you have to use some components from GCC, like libgcc instead of Clang's alternative compiler RT, because Clang can use GCC's version of those tools, but GCC cannot use Clang's, at least not without some serious tricks. Another alternative compiler is tinycc, which is what the name implies. It's just about the smallest possible implementation of a compiler. The source code is smaller than 4 megabytes compared to almost a gigabyte for GCC or Clang, and it takes mere seconds to compile itself. But it doesn't optimize anywhere near as strongly as Clang or GCC. It doesn't support any language other than C. It doesn't have all sorts of other features. So it might be interesting if you're building a small embedded device, or if you need a compiler to embed into your own stuff, and that doesn't need to do anything in particular. But unless you're on a really small device, it probably isn't a good option as the main system compiler. Then, if you are using cross compilers, chances are you've come across both support packages that come with a specific compiler. Unfortunately, those BSPs are usually built around an old version of GCC or an old version of Clang, both of which probably in the meantime have added much better support for the hardware. So unless you're working on a very special device that is not yet supported by upstream compilers at all, it's usually good advice to ignore the BSP and just build your own version of Clang or GCC, or pick one provided by a Linux distribution or so. Sometimes you have to add a couple of kernel patches or so in order to support newer toolchains, but usually this has already been done because other projects have moved on from those compilers. So if you run into a kernel problem building with a newer compiler, try the kernel git repository. And you should really avoid any BSP that is not based on at least GCC version 8 or Clang version 9. Anything older than those is really too old to be useful these days. So conclusions, GCC and Clang are both good options. There's no clear winner. Both have been used to compile full systems, including the kernel. Most Linux distributions are built mostly with GCC. Some of the BSDs are moving towards building mostly with Clang. Pretty much every distribution I've seen makes both compilers available. Some built from source distributions, like Huawei's IoT distribution on Nero, offers both choices for building the entire system. Clang makes it easier to add new architectures and new languages because it has a much more readable code base. It also makes it easier to embed the compiler in your own things. So if you're interested in doing any of that, you may want to give Clang a try. If you're using glibc, you currently need GCC to build it, a bit more on that later. And if you don't need any of the extras offered by Clang, that could be a good reason to stay with GCC, so you end up using the same compiler for everything. So let's look at libcs next. libc provides the standard functionalities that are used by pretty much everything, stuff like strcpy or the likes. And the traditional option is to use glibc. It is by far the most widespread, by far the most complete and standards compliant. It is very well tested, has most complete support for architectures, but its code is not very readable. It's not very optimized for small systems. It's rather big. It takes about 4 megabytes for the important libraries, and it can be built only with GCC. One alternative is musl, which is also almost as complete, pretty fast, relatively small, so less than a fourth the size of glibc. It's designed for newer systems in mind. It supports pretty much all interesting processor targets. Its code is quite readable. It was started in 2011 and only got better since then. So the situation there is somewhat similar as with GCC versus Clang. If you want something that has been around forever, use glibc. If you are looking at a more modern option that was started a lot later and therefore can make use of things that just weren't available at the time glibc got started, you may want to give musl a try. Another interesting option is use libc-ng. It's a complete, fast and relatively small library, 1 megabyte in a full config. One of the interesting things about it is that it can be stripped down easily. So if you're building an embedded system that, for example, doesn't need complicated math functions, you can just strip them out. libc-ng also supports many processor types, including many MMU-less options. Next libc option is klibc, which was written exclusively for the early boot-up process. It's used in initramfs of Debian and a couple of derivatives. It provides only a subset of libc functions. It's optimized for size over performance, and it uses kernel structures directly to avoid type conversions for both performance and size reasons. It's extremely small, fits into 75 kilobytes, but it's probably not powerful enough as a real-world libc. It might be an option for some embedded systems. It uses GPL kernel headers, so the resulting license situation is not 100% clear. You want to avoid it unless you are building a system that is 100% GPL compatible, which of course you should be doing. Another interesting option, or soon to be interesting option, is LLVM libc. It's in early stages. Some code has been published, but it's not complete yet. I don't want to hype a vaporware project, but LLVM has a pretty good track record of delivering something they've announced. Some of the design goals are interesting, like working with sanitizers and fuzz testing, which just didn't exist when the other libcs were started. Targeting C17 and up. Design goal being using source-based implementations instead of writing manual assembly. fixing the compiler to generate code that is as optimized as the assembly language implementations. So it's not there yet, but it may be a good option in the future. Last glibc option that is a serious consideration is Bionic, which comes from Android. It's originally based on a BSD libc. Currently supports ARM and x86 targets, both in 32 and 64-bit variants. It's quite well optimized because of vendor support for Android. Used to be unusable for a regular Linux system because it lacked some functionality needed for X11, but it has caught up on that. Unfortunately, at the same time, they've added some Androidisms that make it pretty hard to compile Bionic outside of the Android source tree, outside of a system that implements some Android-specific functionality. But it potentially makes it possible to use some Android drivers in a regular Linux system without having to go through stuff like libhybrids, and it may be an interesting option to build a Linux Android hybrid system. Potential other options include newlib and dialibc, but they have drawbacks that don't really make them suitable for most users. Conclusions. There's a couple of interesting options. If you need maximum compatibility with other systems, glibc is your only option. If you need a full-fledged but smaller and more efficient library, try musl. If you need a subset and want to strip out unneeded components, try glibc. And if you want to experiment with Android features, try Bionic. Last topic of this talk is C++ support. libstdc++ is what GCC uses as its STL implementation, and that is used by pretty much all the Linux distributions with the notable exception of Android, even by distributions that otherwise use Clang as their primary compiler. And this is what pretty much everything was developed against, simply because it's much older. So if you expect everything to compile without having to add a couple of missing includes or small tweaks like that, you want to use libstdc++. But libc++, which comes out of the LLVM Clang world, is newer and smaller, carries less craft, and most benchmarks also show it performing better. But the problem is, and that's why most distributions aren't using it, you cannot mix libstdc++ and libc++. They export the same symbols, but they're not ABI compatible. And so if you do things like build Qt against libc++ and then run a binary that uses a Qt and was built on a system that has Qt with libstdc++, that's going to crash. But libc++ is increasingly used by third-party applications like Chromium. And if you know that you will never run binaries built on another system, it is definitely an interesting option. uclibc++ is or was another attempt that went with uclibc, but its last commit has been in 2016, so it's probably not a good idea to use this. So, conclusion, if binary compatibility is a big concern, go with libstdc++. If it isn't a big concern and you are using Clang, you probably want to give libc++ a try. And there's no real other options here. Now, that ends the talk about toolchains. If you have any questions or feedback, or of course bags of cash for me, just contact me at one of my email addresses below and check out my favorite projects. Thank you for your attention.